Hey everybody, welcome to Algebra 1-2, Section 10-2, Part 2. Part 1 was all about simplifying radicals, both with just regular numbers and with variables. So today we're going to expand on that and talk about how to do it when you have two different radicals that you're multiplying or dealing with fractions inside of a radical. So by the end of this lesson, you should be able to multiply and simplify radicals. Also, simplify radicals with fractions. So let's talk about multiplying fractions, or multiplying radicals, I should say. So you remember in the last lesson, we took the square root of 50, and then we split it up into the square root of 25 and the square root of 2. And then, of course, simplified it to 5 times the square root of 2. And that was how we simplified that radical. Well, when we split it up, we divided the 50 into 25 times 2. So the opposite is also true. If I have the square root of 25 times the square root of 2, I can multiply those back together and get the square root of 50. So if I have two different radicals, I can go ahead and just multiply what's underneath the radical. So here I have 6 problems that I want to go through and use that same idea. So let's start off real easy. We've got the square root of 3 times the square root of 12. So if I multiply what's underneath the square root, I get the square root of 36, which in turn just turns into 6. So that's the answer to that one. Let's try another one. Square root of 5 times the square root of 10. When I multiply what's underneath the square root, I get the square root of 50, which, as we know from the previous couple slides, just turns into 5 times the square root of 2. Now, on this one, I've got some numbers on the inside of the square root and some numbers on the outside of the square root. So the rule of thumb here is stuff on the outside can multiply together and stuff on the inside can multiply together. So I can multiply the 4 and the 3 and make 12, and then multiply the 8 and the 6 and get 48. So 12 on the outside, 48 on the inside. But of course, you always want to double check, can that be simplified anymore? So I'm going to break down the square root of 48. See, I can split that up into 8 and 6, and then 8 can split into 4 times 2, 6 can split into 2 times 3. The 2, 2, and the 3, those are all prime numbers, so I'll leave that as is. The 4 can break down into 2 and 2, and those are both prime numbers. So I have it completely broken down into its prime factorization, so let's go ahead and organize it underneath the square root. Notice I still keep that 12 on the outside. Okay, so then I can take one group of 2 and move that to the outside. Remember, only one of them makes it on the outside. I could also take another group of 2 and move that to the outside. Remember, only 1 2 makes it out. And that 3 doesn't have a partner, so it has to stay inside the square root jail. So on the outside, I've got 2 times 2 times 12, which is 4 times 12, so 48. And that square root of 3 stays square root of 3. Now, the fact that this is a 48 underneath the square root and the fact that this is a 48 outside the square root, completely coincidence. Okay, they have no correlation there. So don't get any ideas that, oh, you just take what's there and you put it out there. It doesn't work like that. So let's go ahead and do that same type of problem. Now, I can go ahead and multiply the 7 times the 8 because they're both on the outside, and I can get 56. And then I can multiply the 18 and the 22, and I can get some big number, probably somewhere close to 400. And then I've got to break that 400 down. So here's a little heads up. If you're going to multiply the 18 and the 22 just to break it apart again, do I even need to know what that big number is? Or can I just bring down the 18 times the 22 and then break down the 18 and break down the 22? Let's do that. So 18 can break down into 9 times 2. 22 can break down into 2 times 11. The 2's and the 11's are prime numbers. The 9, let's break that down to 3 and 3. Those are both prime numbers. So if I organize this all underneath the square root, I get 56 on the outside, and then 2 3's, 2 2's, and 11 on the inside. Now, I've already crossed off a group of 3's. Those can move to the outside. And again, only one of them makes it. That group of 2's can try to escape, but only one of them makes it. And that 11 does not have a partner, so it has to stay in there. So 2 times 3 times 56, that's 6 times 56, that's 336 times the square root of 11. Okay? Now let's try a problem that doesn't have numbers, it just has variables and exponents. So if you recall, if I multiply two variables that have the same base, all I have to do is add up the exponent. So x to the 4th and x to the 8th, if I multiply those, I get x to the 12th. And then y to the 7th, y to the 13th makes y to the 20th. So now that I've got that underneath one radical, what I can do now is I can go ahead and figure out the square root by taking half of the exponent. So x to the 12th turns into x to the 6th, y to the 20th turns into y to the 10th, with no square root on it. I've already used the square root to go from 12 and 20 to 6 and 10. So x to the 6th, y to the 10th, that's my final answer on that one. Now here we've got everything all just jammed together in one problem. So this is going to be a little bit of a handful. My advice, because there's so much going on, just take one thing at a time. So I'll multiply the two numbers on the outside and I get 20. And then let's go ahead and multiply the numbers on the inside. Well, 18 times 14, I'm not sure what that'll be, but I'm just going to break it apart anyway. So let's just go ahead and break down the 18, break down the 14. 18 can break down into 6 times 3. 14 can break down into 2 times 7. The 3, the 2, and the 7, those are all prime numbers. And then the 6 can break down into 2 times 3. Those are prime numbers. So let's organize it. 20 times the square root of 2 times 2 times 3 times 3 times 7. So that group of 2's can escape and make a single 2 on the outside. That group of 3 can escape and make a single 3 on the outside. And the 7 has to stay put. So 3 times 2 times 12, that's 120. So I get 120 times the square root of 7. But that's just dealing with the numbers. I haven't even touched the x's yet. So let's go ahead and multiply that. So I've got x to the 3rd and x to the 12th. That makes x to the 15th. So now let's deal with that. So if you recall from our previous lesson, the way we deal with that is we divide by 2. And since this is an odd number, I'm going to have one remainder. So 2 goes evenly into 15 7 times. So I'll put x to the 7th on the outside of the square root, with 1 remaining left on the inside of the square root. So it looks like I've taken care of all the pieces there. There was a lot going on there. So my final answer is going to be 120 x to the 7th times the square root of 7x. Let's do a few more examples and just kind of get a better handle on this. Okay, so we're just going to do 4 problems here real quick. So square root of 6 times 4 square root of 6. That 4 is going to stay on the outside. And then the square root of 6 times the square root of 6 is going to be square root of 36. Which, as you know, the square root of 36 is just 6. So this whole problem just boils down to 24. Nice and easy. Number 2, that negative is going to stay on the outside. And then 5 times 20 is 100. And so square root of 100 is 10, so that's just going to make negative 10. So we've talked about you can't take the square root of a negative number. What's underneath the square root is positive. It's okay to have a negative number on the outside of the square root. All right, number 3, negative square root of 2 times square root of 3. That negative stays on the outside. Square root of 2 times square root of 3 is square root of 6. And if I go to simplify that, it only breaks down to 2 and 3, and nothing has a partner, so nothing escapes. So that's just my final answer there. Last question. That 4 stays on the outside. Square root of 8 times the square root of 2, that's going to make the square root of 16. And square root of 16 is 4. So it boils down to 4 times 4, which is 16. So these are slightly different than the ones that we did in the fact that it's a little bit easier. Once we multiplied and got our square root, they mostly turned out to be whole numbers. So they can be this easy or they can be complicated like that purple problem on the slideshow. But I just want to get you to have a feel for how to do these types of problems. So next, let's talk about how to deal with dividing or having fractions inside of a radical. All right, so let's say that we've got a radical with fractions inside of it. We're going to see 3 different scenarios here. One, what happens if both the numerator and denominator are both perfect squares? What happens when just the denominator is a perfect square? And what happens when neither number is a perfect square? All right, let's go ahead and take a look at a few examples and see how that goes. All right, so first question, the square root of 49 over 81. Both of those are perfect squares. Well, that's probably the best case scenario because we can just take the square root of both of those. If it helps to visualize it, we can write it as the square root of 49 over the square root of 81. So the square root of 49 is 7, and the square root of 81 is 9. And that's my final answer, 7 over 9. Similar idea on the next question. So square root of 9 is 3, and the square root of 16 is 4. Boom, 3/4. Problem done. We can do something similar on the third problem here. 1's a perfect square, 100 is a perfect square. So square root of 1 is 1, square root of 100 is 10. Now take a look at this. The next problem, square root of 40 over 81. The numerator is not a perfect square, but the denominator is. And that's the main thing that we want when we work with fractions is we do not want a square root on the denominator. Okay, let's get that denominator to be a whole number at all costs. So if I see square root of 81 is 9, so that's good. I like that. Let's go ahead and break down the square root of 40. For the sake of time, I'll do that in my head. That's the square root of 4 times the square root of 10. So that's going to be square root of 4 is 2 times the square root of 10. And last thing I want to do is I want to double check. Can anything reduce? So 2 over 9 can't reduce. So that's my final answer, 2 square root of 10 over 9. Okay, it's okay to have a square root in the numerator, but do not leave square root in the denominator in your final answer. They'll be counted wrong every time. Similar idea on the next question. So square root of 3 over square root of 25. Square root of 3 just stays square root of 3. Square root of 25 is 5. Boom, problem done. All right, next question. Oh, we throw some variables in here. Looks like neither one of those are perfect squares. But something I can do is double check. Can anything reduce? Before we even start messing with the perfect square, let's see if we can reduce. 18 and 32. 2 can go into both of those. So that reduces down to 9. And that reduces down to 16. And then let's reduce the x's. I've got 3 x's on top, 2 x's on bottom. So if I do a little bit of canceling, I get a single x up on top. Now, if I try to simplify that, the square root of 9 is 3, but that x stays underneath the square root. Because that x doesn't have a partner, it can't escape, it can't do anything. So it stays under the square root. And square root of 16 is just 4. So final answer on that. Now let's try a few other problems. All right, square root of 5/7. 5's not a perfect square. 7's not a perfect square. 5 and 7 can't reduce. So all the tricks that we've learned so far, nothing's working. There's no way to get that 7 to be a whole number unless we do a process called rationalizing the denominator. It's a process where we take that denominator and magically turn it into a whole number. And here's how we do it. In order to turn 7 into a perfect square, how about we multiply it by itself? And of course, whatever I do to the denominator, I have to do to the numerator. So I'll multiply by 7 there. So now I have the square root of 35. That's an ugly 5. And 7 times 7 is 49. So the whole purpose that we did that was to get our denominator to become a perfect square. So now square root of 35 can only break down into 5 and 7, and neither one of those is a perfect square, or neither one of those has a partner, I should say. So square root of 35 stays the square root of 35, and the square root of 49 is 7. So there we go. We have our final answer because there's no square root in the denominator. It's still a fraction. It still doesn't look pretty, but ultimately we do not want a square root in the denominator. All right, square root of 8 over 3. Let's see, can anything reduce? 8 over 3 does not reduce. So let's rationalize the denominator. Let's multiply that 3 by itself. And of course, what you do to the denominator, you have to do to the numerator. So now I've got square root of 24 over the square root of 9. Square root of 24, if I were to jailbreak that, that would be 2 times 2 times 3. So I'd have a group of 2 escape. Only one of them makes it on the outside. And then there's a 3 left underneath. Let's see, is that right? No, it's not, because it's 2 times 2 times 2 times 3. So there'd be a group of 2 on the outside and a 2 and the 3 on the inside. So that makes 6. Okay, glad I caught myself. And then the square root of 9 is 3. So double check, can anything reduce? The 2 and the 3 can't reduce. Some people might say, oh, well, the square root of 6 and the 3, that can reduce. 6 and 3 can reduce by 3. But the 6 is underneath the square root and the 3 is not. So they can't interact. Okay? So I think that's my final answer. 2 square root of 6 over 3. Last problem. Okay, square root of 45 over 2x, nothing reduces. So let's go ahead and multiply the denominator by itself. So 2x here and 2x there. That gives me the square root of 90x over 4x squared. And again, the whole purpose of doing that is to turn that denominator into a perfect square. All right, let's go ahead and break down the 90. So 9 times 10, 3 times 3, 5 times 2. So I've got 3 times 3 times 5 times 2. And I can go ahead and put that x in there. So I see a group of 3. Those can escape and make a single 3 on the outside. The 5, the 2, and the x, none of them have a partner, so they all have to stay on the inside. And I can multiply that and make it 10x. So then my new numerator is 3 on the outside and 10x on the inside. And then my new denominator, 4x squared is a perfect square. Square root of 4 is 2. Square root of x squared is x. So that was kind of a tricky one. And the answer is still pretty ugly, but that's as simple as we can make it. So 3 times the square root of 10x, and then all that is over 2x. Let's double check. Can anything reduce? The 3 and the 2 can't. Some people might say the 2 and the 10 can reduce, and then the x's can reduce, but that's not true because the 10x is underneath the square root, and the 2x is not. So they can't interact. So I think that's my final answer there, is 3 square root of 10x over 2x. Now, I know this can be tricky, and I know there's lots of places to mess up, but the more you practice, the better you're going to get at it. So if you guys have any questions, please feel free to ask me in class, shoot me an email, and I'll be glad to help out in any way that I can. I hope you guys have a great day, and I will see you real soon. Have a good one.